All right, folks, so we are back. We are at the very last section of talking about the evidence approximation, and we're going to talk about this quantity gamma that came up in the previous section, and it has a really cool interpretation, which I think kind of generalizes beyond our discussion here into kind of the effective number of parameters that are determined by our data. And the way we're going to see that is by considering how our estimates of the parameters, the W's, are related to their maximum likelihood value through gamma, basically. Okay. I had to actually, when I was reading this, I had to actually unpack the material here. So I would actually refer you to my notes. Let me show you those notes. So let me see if I can move the. There you go. So you can see in my notes there's going to be I have a section on this where I unpack some of what's going on here. We'll do that together now, but if you want to see it kind of in writing, it's there as well. So okay, so let's go back to the book. So there we are. Okay, so now the idea is, yeah. So okay, so let's just read. So consider the contours of the likelihood function and the prior as illustrated in 3.15. Okay, so this is the whole idea is just here. So let me zoom in, make sure you guys can see. Okay. So remember that this is the likelihood of the weights. So we've got, here it is, we've got log of p of t given our weights, and I think there's a beta term. Is going to be, just including just the terms in, going to be 1 over 2, and there's a beta on top, the precision, times, right. Okay, and so now if we kind of expand this out, we're going to get, this is going to be something like minus 1/2 of, and if we kind of complete the square, so we want to get W on its own, we're going to get that this is going to be centered on, it's going to be kind of contour centered on this maximum likelihood estimate. And I'm going to put the beta, you see that's going to come from the phi and the betas interacting, W minus WML. So you guys can see that. Okay, very good. So that's kind of, so now what we can do is, so that's kind of what he's talking about the contours of the maximum likelihood of the likelihood function. So what we're going to do is we're always going to do the same trick we always do. So we're going to write this as do the eigen decomposition, and it's going to be equal to u times lambda times u transpose. And so we're going to put that in here, and so we're going to do W minus WML. So you're just kind of switching coordinates to, and now we'll just, so we're going to rotate everything. So we'll just rotate our coordinates for the weights as well. And we'll just write them as, whatever, we can put it in these rotated coordinates. Again, we've decoupled everything, which is always the point of doing this decomposition. Okay, so that's what we have. And so we can write this as, everything's decoupled now, there's just a diagonal matrix. So it's going to be equal to minus 1/2 sum on I is equal to 1 to m of W hat I minus W hat ML squared times lambda I. So you can see that these lambda i's are somehow kind of measuring how strongly each of those parameters is being pulled towards its maximum likelihood value. Okay, so now what's going to come up next is, well, what happens when we bring in, we don't have just the likelihood, we actually also have the prior. But our prior is spherical, so we can also kind of switch coordinates, rotate everything by u, and it's no problem. So, so we can, when we do that, I'm just thinking what I should erase here. Okay, so let me just erase all of this stuff. Yeah, I'll write that up here again as well. B phi t phi u transpose. Okay, so now what if we add in? So now we don't have just the just the prior, but we also have the likelihood. So let's say we added in a minus 1/2 alpha w transpose w. Right. Well, we can kind of equivalently switch coordinates when we switch coordinates to the UU coordinates. Well, we can write this as is equal to minus 1/2 alpha wt whatever u transpose w, and then this is just this just becomes alpha w. Okay, so that's just to show you that we can just, because, and this is really crucial, because our prior is spherical, we can also rotate its coordinates to match up, to line up with those of the likelihood. And now we get, when we add it in, we get this additional term. We get this 1/2 alpha wi squared. Okay, so we've got that. So now let's pull that out. So let's now erase some of these items. There we go. Okay, cool. So now this is our that should be our log p w given t, right? This is the posterior. And so now we're going to want to figure out what our weights are. Well, we're going to take the let's take the derivative. So we just do the wi hat, and what do we get? Well, this is going to equal the wi only shows up. Oh, this should be I. Wi only shows up in the ith term of the sum, so we're just going to get minus wi minus wml I times lambda I minus this contribution from the prior. All right, so now if we just rearrange this, this goes to, well, wi hat is actually just going to equal to lambda I over lambda I plus alpha times wi ml. And that's the key equation there. So you see that what's happening is that our ith parameter in these rotated coordinates is going to be set to the maximum likelihood estimate, but then kind of shrunk according to these eigenvalues. So if these eigenvalues are large, then it means that we have a lot of precision. The data gives a lot of precision, so our value of that parameter is going to be actually close to its maximum likelihood value. But if these lambda i's are small, the precision is low, then this term is going to be small, and these weights are going to be pulled towards their prior value, so towards 0 in this case. And so this quantity here, which shows up in the terms of gamma, is kind of like counting like how well the data is determining each of the parameters. What are the effective number of parameters? So that's kind of what this whole thing is about. So now I think we can go back, and again, I've got the details of this are also in my notes, so you can have a look there. But that's kind of what we're talking about here. So again, like if you look at this particular example, it looks like in this direction we don't have a lot of precision, right? So our lambda I is small, which means that our value, the map estimate is actually going to be pulled towards, you see, in this coordinate, it's going to be pulled strongly towards this prior value, which is 0. But in this coordinate, we have a lot of precision, so you can see that the curvature is high. And so the map value is actually very close to the maximum likelihood value. So in this direction, whatever it is, we have a lot of, the data is really constraining us. So the map value is in that coordinate, in the kind of y coordinate, is very close to the maximum likelihood value. That's kind of what this is all about. Okay, so now let's read the section. So the result 3.92, which is what it's talking about. Yeah, this one. Okay. Has an elegant interpretation which provides insight into the Bayesian solution for alpha. So consider the contour of the likelihood function. This is kind of what we're talking about. Here we've implicitly transformed to a rotated set of axes in parameter space aligned with the eigenvectors ui. So that's what we did, right? That was when we switched everything to these u coordinates. Contours of the likelihood function are then axis-aligned ellipses. The eigenvalues measure the curvature of the likelihood function, and so in figure 3.15, the eigenvalue lambda 1, which is in this direction, is small compared with lambda 2. Because the curvature corresponds to a greater elongation in the contours of the likelihood function. Okay, so this is going to be one of those directions that's kind of not well determined by the data. Because beta phi is a positive definite matrix, it will have positive eigenvalues, and so the ratio will lie between 0 and 1, right? These are all positive, and alpha is positive. The quantity gamma will lie in the range 0, gamma m. And now, this is kind of getting into our discussion. For directions in which lambda I is much greater than alpha, the corresponding parameter wi will be close to its maximum likelihood value, right? So in these directions, where in this particular direction, we're kind of, we have a kind of very small error bars around WML, so we kind of, the data constrains it a lot. We're going to be pulling WMAP's coordinate up that way. For directions in which the will be close to its maximum likelihood value and the ratio will be close to 1, such parameters are called well determined. So let's highlight that. Right. Because their values are tightly constrained by the data. Conversely, for directions in which lambda I is much less than alpha, this precision is kind of providing the scale, the corresponding parameters will be close to 0. And they're close to 0 because our prior was that the prior value was 0. So in general, it'll be close to whatever the prior value is. These are directions in which the likelihood function is relatively insensitive to the parameter value, and so the parameter has been set to a small value by the prior, right? So we have this like huge error bar. It's like, well, let's just pull it to 0. We won't take a penalty if we do. The quantity gamma therefore measures the effective total number of well-determined parameters. So that's kind of that's the important idea. So I think this was kind of quite a cool interpretation. It also allowed us to kind of like talk about a bit more about what this quantity here means, what its eigenvalues mean, in relation to those of the prior. And I think that really having those two pieces together, I think really kind of gelled what's going on here, for me at least. Okay. And so now we can obtain some insight into the result 3.95 for reestimating beta. So let's look at, what was that one? This was this. And notice again, essentially what we're doing is we're computing, beta was a precision of the residuals, right? The goodness of fit residuals. And so if this was just a 1 over n, that would just be kind of their variance, modulus and biases. But notice that we've got this minus gamma. So we're actually we're modifying it by the effective number of parameters, which is what he's going to mention now. So by reestimating and by comparing it with the maximum likelihood result, both these formulae express the variance as an average of the squared difference between the targets and the model prediction. So that's kind of what this is. The average of, which is kind of a formula for variance, you just take some quantity minus its mean and divide by the number of items you're adding up. But we've got this kind of this adjustment term. Okay. However, they differ in the number in that the number of data points and the denominator of the maximum likelihood result, which is in 3.21, is replaced by n minus gamma in the Bayesian result. So we recall from the maximum likelihood estimate of the variance for a Gaussian distribution over a single variable is this, right? Again, finding the deviation around their mean value, dividing by 1 over n. But its estimate is biased because we've used the data itself to estimate mu, and so to accommodate that, we actually end up getting adjusting this n to n minus 1. And so it says, look, we're going to see that this is going to be obtained from a Bayesian treatment in which we marginalize over the unknown mean. Okay, so it says, look, the factor n minus 1 in the denominator of the Bayesian result takes account of the fact that 1 degree of freedom has been used in fitting the mean and removes the bias of the maximum likelihood. Now let's look at what's happening in our case. Consider the corresponding results of the linear regression model. The mean of the target distribution is given by this thing, so the linear combination of the features. which contain m parameters. However, not all of these parameters, okay, so the mean of the target distribution, however, not all the parameters are tuned to the data. The effective number of parameters is actually determined by gamma, which is between 0 and m. So let's just highlight. So with the remaining m minus gamma parameters set to small values by the prior. So this is reflected in the Bayesian result for the variance that has a factor n minus gamma in the denominator, thereby correcting for the bias of the maximum likelihood result. Right. So we're kind of getting this natural correction. It's not -1, it's just going to be determined on, however many parameters we have. In this particular case, there was just one, but, and even in this case, maybe we'll see later on, like maybe your data doesn't fully determine, maybe this value should be even, less than 1, right? It sure can be. So that'd be interesting to see. But the point is that, in this, so there's 1 over beta, it's kind of like the variance of the residuals. And we're seeing that it's getting adjusted by some quantity that reflects, kind of naturally reflects the effective number of parameters we've estimated from the data, and that we need to then subtract to kind of get an unbiased estimate. Okay. Now in the next couple of sections, I think he just goes and shows sort of how this procedure works. I think one thing that's kind of was missing for me in this section was, okay, so we've done all of this stuff. We've come up with our approach of okay, we're going to maximize the evidence function. We're going to replace it. How well does it do it? So how well do we actually go and how well do we actually approximate that integral we're interested in? Now, obviously, the reason why we're approximating is because we can't compute it directly in at least in the full case we're interested in. But it would have been useful to, at least in some toy cases, look at how well the approximation works. Look at the distribution, this approximate distribution we get, compare it to the true distribution that we would have worked out in a toy example, fully numerically, if we needed to, and see how well it does. He doesn't quite do that here. So I think that's a bit missing, and I talk about that in my notes. But let's have a look at what he does do. Okay. So by setting the parameters using the sinusoidal synthetic data that we always work with, together with the Gaussian basis function model comprising 9 basis functions, total number of parameters is 10, including the bias. We've set beta to its true value again. So again, we're not estimating beta. We're just going to use the evidence framework to determine alpha, as shown in figure 3.16. So I don't think you guys can quite see this. That's kind of what's going on here, basically. So what he is doing is, so there's kind of the gamma for different values of, in this case, ln alpha, doesn't matter. And this term 2 alpha for which I think it came up when we were estimating alpha iteratively. And then the intersection kind of tells you what the optimal value of alpha should be. And then in this next curve, in this next plot, he's kind of showing what the performance is. So this is the location of the log evidence, which is maximized at exactly this location, and then he's comparing it. So his measure of like the goodness, how well this procedure performed, is comparing it to the generalization error. So the error when you have kind of when you leave out some data, and estimate your parameters and try to predict on the left out data. And you can see the idea is that, look, if you pick this location for alpha, well, you're pretty close to the optimum value of the generalization error. So you don't have to kind of go through all those steps, having a cross-validation set to try and then figure out alpha. You can actually just figure out alpha on your training set, and that value will actually will be pretty good. And that's pretty nice. I mean, it's kind of a nice property, I suppose. But again, I think it would have been really useful to go and say, okay, well, how well did we actually approximate that integral that initially we were interested in, that predictive integral, right? Because that's initially what we were interested in. I mean, it's possible that, like, you can imagine a setting where, because our model is so restrictive, our predictive distribution is actually not very good. And we still want to, the whole point of this procedure is to actually approximate that predictive distribution. So just the fact that we get kind of good generalization error, it's not exactly the same thing. And I talk about this more in my notes, so you can have a look there if you're interested in that. But anyway, it seems like, at least in this kind of toy example, if we kind of did this procedure, we would do basically about as well as we would do if we had kind of left out some data and did the whole cross-validation procedure for estimating, for estimating our parameters. And yeah, and having good generalization error. Okay, so that's kind of what he's talking about here. We also see how, oh yeah, and there's one other piece that he talks about, which again, I think it's, yeah. So here what he's doing is, in this particular figure, he is changing, so alpha and then correspondingly gamma. So he says, okay, plot the 10 parameters from the Gaussian basis function model versus the effective number of parameters in which the hyperparameters varied in the range 0 to alpha to 0 to infinity, causing gamma to vary in the range from 0 to m. Again, this is not, I guess this is not very surprising, right? So as you increase your penalty, alpha. So as you increase your penalty from, let's say, 0, which would be kind of towards this end, all the way to infinity, well, you would get that your weights are shrinking, which is essentially what we see. Maybe the interesting aspect is that, well, you can actually interpret alpha, that instead of having alpha, you can actually interpret things in terms of gamma, which is your effective number of parameters. And you can see that, as alpha is changing, so that gamma is becoming larger and larger, your effective number of parameters is getting larger. Well, more of your actual parameters are being set by the data. They're not getting pulled so much towards the prior. So I think that's essentially what he's trying to show here, that that this effective number of parameters reflects the number of your parameters that are actually being determined by the data and not being squished towards their prior values. So yeah, I guess just confirming what we learned in this section. Finally, yeah, he just says, look, if we have lots of data, then effectively we can assume that our data determine all of the parameters. So we can set gamma to m, and the re-estimation equations then become really simple. So you just get, alpha is, has this particular form. You can think of this as, it's going to be kind of the 1 over alpha is going to be kind of the variance of the maximum likelihood, solution for the weights. And this maximum likelihood, because in the large data limit, the maximum likelihood term is going to dominate the prior. So alpha isn't going to show up in here anymore. It'll just be, you can assume set it to 0 basically, or some very small value. And similarly here. So, and beta is going to be just the variance of the residuals. So you can kind of come up with, if you have lots of data, then actually you can actually estimate your alpha and betas just kind of immediately, and without having to use any kind of cross-validation or anything. You can already just set your hyperparameters from the data directly. So these results can be used as an easy-to-compute approximation to the full evidence re-estimation procedure, because they do not require evaluation of the eigenvalue spectrum of the Hessian. So we didn't have to figure out lambdas or anything like that, because we basically assume that lambdas are so large that the lambda I over lambda I plus alpha is basically 1, and then things kind of simplify. So that can kind of save you having to do cross-validation. You get these hyperparameters directly. But again, the proof is in the pudding. You have to see, does it actually work for your data? And I wish he'd kind of done a bit more of that. So we've done all this work, but there isn't really much in terms of evaluating it. So I think that could have been improved. So that's basically it. That's this bit of an advanced section on the evidence approximation. I think it was useful in its own right. I think there's kind of a few interesting ideas. For example, approximating integrals by approximating integrals by replacing some of the problematic terms with their peak values. That's a trick that comes up all the time. The iterative procedure for finding these solutions to these equations, and that the notion of the effective number of parameters, which I thought was really useful, and I would expect has kind of quite broad applicability. Okay, so I think that's the end of that. And in the very next section, we're going to talk very briefly about limitations of fixed basis functions, and then kind of just wrap up the chapter. So yeah, so thanks for coming along as far as you have, and hopefully I will see you next time when we finish the chapter here. Talk to you then.